Generative AI has driven the marginal cost of software execution to near zero. When autonomous models can instantly write complex code bases and replicate workflows at machine speed, legacy network defenses are simply overwhelmed. Economic value now concentrates in the verifiability layer. When execution is automated and cheap, the premium moves to the cryptographic evidence that a specific digital asset or outcome is authentic. Within this shift, autonomous AI agents have become active economic actors. Empirical data shows they already generate a substantial portion of global internet traffic and are executing high-frequency micropayments across digital ledgers. Yet these agents operate with a structural trust deficit. They lack legal identity, cannot hold capital in traditional banks, and their underlying language models are highly vulnerable to adversarial prompt infections. Legacy blockchains offer no solution. Networks constructed primarily as venues for human retail speculation are structurally unequipped to safely manage autonomous machine capital at scale. This isometric wireframe maps out the exact architecture required to fix this: a secure, decentralized financial operating system specifically engineered for autonomous machines. For an AI to securely hold, manage, and deploy cross-chain assets without human intermediaries, the system requires a trustless foundation built directly into the Layer 1 consensus. Autonomous agents make financial decisions based on data. If the input data is flawed, the execution fails. Traditional Web3 architectures pull this information using external Oracle networks, which introduces a critical point of failure and high latency. This comparative schematic shows how the Flare network resolves this vulnerability by enshrining its data protocols directly inside the proof-of-stake validator consensus ring. The first of these protocols is the Flare Time Series Oracle, or FTSO version 2. It delivers decentralized price and reference data directly to the execution layer. FTSO version 2 scales to support 1,000 parallel asset feeds, utilizing a verifiable random function to sample data from independent providers. The second protocol is the Flare Data Connector, acting as the L1 state connector for off-chain events. When an agent needs to confirm an external event, such as a Web2 API update, independent providers fetch the data and submit fit vectors. Once signatures representing over 50% of the validator weight agree, a Merkle root is committed directly on-chain. By internalizing this verification, the architecture completely eliminates the need for centralized bridge intermediaries. Because these protocols are enshrined, the data provenance inherits the full economic security of the base ledger. Agents receive mathematically immutable truth. Once the data is secured on-chain, the AI logic processing it faces a different bottleneck. Large-scale deep neural networks exceed the gas constraints of on-chain virtual machines, forcing execution off-chain. Moving execution off-chain introduces a direct threat. A host operating system or a cloud administrator could maliciously alter the agent's code or inject unauthorized prompts without detection. This cross-section shows a confidential virtual machine. To hardware isolate the trust boundary from the parent OS, developers deploy trusted execution environments powered by processors like Intel TDX or AMD SEV SNP. The challenge is protecting the startup sequence. During measured boot, firmware measures the kernel and initial RAM disk, generating a unique hash. The file system remains encrypted until a remote key broker verifies this hash and releases the decryption keys. This sequence generates a virtual trusted platform module attestation, which serves as physical, verifiable proof that the enclave's code executed exactly as programmed. Trusted execution environments provide the autonomous agent with a tamper-proof off-chain brain, securely linked to the L1 ledger without requiring trust in the cloud provider. A secure agent isolated on Flare still faces a cross-chain problem. How can it command legacy, non-smart contract assets like Bitcoin or Xrp without relying on a centralized custodian? The solution is the protocol-managed wallet. In this setup, private signing keys for external chains are generated and held exclusively within the secure hardware enclaves. The enclave is programmatically bound during the measured boot process. It is hard-coded to sign external transactions only when it receives a cryptographically verified consensus instruction directly from the Flare validators. However, a single enclave architecture carries operational risks. A localized power outage creates downtime, and a manufacturer-specific hardware exploit could compromise the isolated private key. Flare mitigates this with a multi-TEE consensus quorum, utilizing different chips from distinct manufacturers. An external transaction will only execute if it receives an M of N threshold signature combined from multiple independent, globally distributed enclaves. This architecture drives the F-asset system. Agents can lock external legacy assets on their native chains and trustlessly mint them as programmable utility tokens on the Flare network. Multi-TEE consensus turns physical hardware enclaves into decentralized cryptographic bridges, granting autonomous agents secure financial reach across the broader digital economy. To participate in decentralized finance, agents must hold collateral, but forcing thousands of distinct agents to manage their own individual private keys introduces high theft risks and severe operational friction. Isolated wallets require extreme over-collateralization to remain safe against price volatility, which limits the capital efficiency of an autonomous swarm. This split screen shows how the Denarii core vault resolves this inefficiency. It acts as a treasury operating system that pools agent collateral into a single environment. By securing assets within a shared, non-custodial multi-sig account, the system structurally prevents unilateral theft by any single compromised agent. The system implements rigorous risk mitigation layers to protect the programmable tokens minted against this collateral, beginning with strict global minting caps. The system continuously monitors the collateral ratio of every agent using real-time price feeds from the Flare time series oracle. If an agent's ratio drops below the critical liquidation threshold, a smart contract programmatically liquidates their holdings to protect the vault's solvency. The core vault architecture upgrades agents from isolated scripts carrying counterparty risk into sovereign economic participants, backed by institutional-grade capital efficiency. This fully populated matrix maps the end-to-end verification pipeline as an integrated system. At the base, the Layer 1 blockchain provides the immutable settlement bedrock, complete with enshrined Oracle data feeds that cannot be manipulated by third parties. Above that, the hardware enclaves and multi-T managed wallets execute the agent's complex off-chain logic within an isolated, verified runtime. This pipeline generates deterministic data proofs and action proofs, finalizing every state change into a permanent audit trail. This decentralized architecture replaces legacy models that rely on implicit network trust and human intermediaries. By making this complex cryptographic infrastructure invisible to the user, platforms remove the primary barrier to adoption, allowing autonomous agents to operate as the default treasury for the digital economy. The resulting economy operates on decentralized truth, where financial sovereignty is enforced by mathematics rather than centralized authorities. This fully populated matrix maps the end-to-end verification pipeline as an integrated system. At the base, the Layer 1 blockchain provides the immutable settlement bedrock, complete with enshrined Oracle data feeds that cannot be manipulated by third parties. Above that, the hardware enclaves and multi-TE managed wallets execute the agent's complex off-chain logic within an isolated, verified runtime. This pipeline generates deterministic data proofs and action proofs, finalizing every state change into a permanent audit trail. This decentralized architecture replaces legacy models that rely on implicit network trust and human intermediaries. By making this complex cryptographic infrastructure invisible to the user, platforms remove the primary barrier to adoption, allowing autonomous agents to operate as the default treasury for the digital economy. The resulting economy operates on decentralized truth, where financial sovereignty is enforced by mathematics rather than centralized authorities.